Okay, well, here we go. Let's start off with this wavelength of matter concept, and let's see what that looks like. So momentum, lowercase p, is given by Planck's constant divided by the wavelength. So let's just try this example really quick. Let's suppose that we're talking about the momentum of an electron. And so let's suppose that we have an electron that's traveling.
Professor Chase,
Yeah,
it's a little out of focus.
yeah, what's up with that? Thank you.
Thank you.
Now it's upside down. Yeah. Ooh, super. Whoa. Well, that's all kinds of fun, isn't it? Okay, so we're going back to normal. Yay! Okay, so we have this electron chugging along. They usually go pretty quick. So let's suppose it's doing something like 5,000 meters per second. And we want to find out what the wavelength is going to be. So let's solve this for wavelength. H over P, and momentum is just mass times velocity, just like it was in physics 1. And the mass for an electron is 1.6 times 10 to the minus 31 kilograms. Okay, great. Let's see what you get for the wavelength. The value for Planck's constant that we need to use is not the one that's in electron volts that I asked you to write down, but H is 6.636 times 10 to the minus 34. And then we have 1.6 times 10 to the negative 31 and 5,000. Okay, great. Okay, let's see. Let's see if I put the light on, if we can see my calculator a little bit better. Okay, so it comes out to be about 8.3 times 10 to the minus 7. Oh, that's a good example. In meters, but we've been talking about nanometers of light, so that would be 130 nanometers. Which you could set up an experiment that would...
I did it, I got 7.95 times 10 to the negative 7. What do you think the difference, like it's very close, but like what do you think where that difference came from? Because I did it a second time and I still got the same answer.
So let's go through and take a look at the numbers I got on my calculator. So 6.63.
And now I have the right answer.
Okay. All
I
right.
think I typed 0.363 instead of 636.
Gotcha. Okay, so you could definitely set up an experiment that would be able to detect that this wavelength. So 830 nanometers is in the infrared range. So pretty low momentum for an electron. So let's replace it now. Let's do another example, and let's do the momentum of a car. And so this one's for you. So now we have a car, and the car has, whiteboard's still wet. Okay. That's not working. Okay. The car. And we'll give the car small car, so 1,000 kilograms. Beep, beep. And it's going at 30 meters per second. And find its wavelength. So wavelength equals Planck's constant over momentum, which is mass times velocity. Okay, go ahead. Let's see if you can do this. Okay, so this is what I got. Which is, whoops, that's okay. Which is very small, and it would be very challenging. Since this is much, much smaller than the nucleus of an atom, it would be hard to ever come up with an experiment that would be able to detect this. All right, so what do you think? Thumbs up? Doing okay? Awesome. Okay. So let's take a look at a transition between energy levels. So we need to take a look at so we start off, and we're just talking about the hydrogen atom, the Bohr atom. So the energy level is going to be predicted by minus 13.6 electron volts divided by n squared. That didn't come out very well. Good. So a prompt might look something like this. Find the wavelength that corresponds to for n equals 2, transitioning to n equals 6. All right, so the way I recommend doing this is that you calculate them separately. And so we'll take this in pieces. We'll go this way for n equals 2, and we'll go this way. And then also, let's put the minus sign off to the side for a second. So, because we can deal with that later. So that makes this not so bad. So 13.6 divided by 2 squared. And again, this is in electron volts. And then we do 13.6 over 6 squared. Okay, so this is 3.4 electron volts. And this is only 0.38 electron volts. So we take the difference between the two. Okay. Now, it doesn't really matter about the minus signs, because we can do this in an absolute value sense. The main idea is we want to find out what is the energy for that photon going to be. So if we do a transition that goes from n equals 2 to n equals 6, then our atom is going to absorb a photon that has this much energy. If the transition's from 6 down to 2, then our atom is going to emit a photon with this much energy. So now the next step is to calculate the wavelength. And we set that equal to the energy for the photon. So this is equal to E, which is equal to hc over wavelength. And this time we will use that constant that we talked about before. So h is equal to, I'll write it over here, 4.141 times 10 to the minus 15 electron volt dot seconds. And we're solving for wavelength, so we'll rearrange this equation. Wavelength is equal to hc over the energy level. And Planck's constant, 4.141 times 10 to the minus 15. And then speed of light, it's everywhere. 3 times 10 to the 8, really big number. And then the energy level, which is 3.02. And the units are all going to work out, so we don't have to worry about that too much. Just this lefty keeps putting his hand on stuff he wrote down. Super annoying. Okay. Let's see. Was I smart enough to put H in for, well, look at that. Okay, so was I smart enough to put C in also? What? Look at that. Okay, so we're going to do H times C and then divide that by 3.02. My gosh, that's super easy, isn't it? Okay, so we get 4.11 times 10 to the minus 7 meters, and that's equal to 411 nanometers, which is blue. Okay. So, questions about that? All right. I don't really think you need to do another example. It'll come in the form of a quiz. Okay. All right, so nice to see you all. And I'm going to end the video at this point and stop recording.